class, we started talking about aldehydes and ketones and reactions of aldehydes and ketones. And a lot of our reaction focus was on these nucleophilic addition reactions because aldehydes and ketones play the role of electrophiles, right? They have that electrophilic carbonyl carbon. So if we react them with some nucleophile, right, negative charge here, or our Grignard, we know that carbon has a lot of electron density. We get this new bond between our electrophilic carbonyl carbon and whatever our nucleophile is. All right, so our nucleophile adds to that electrophilic carbonyl carbon, nucleophilic addition. Okay, and where we left off was talking about nitrogen. So first of all, when we're talking about our reaction mechanisms, we talked about acidic and basic conditions. Under acidic conditions, you shouldn't have any negative charges. Under basic conditions, you shouldn't have any positive charges. But we said nitrogens are weird, and they react under these neutral conditions where they have both positive and negatively charged intermediates. All right, so this is where we left off, which is the nucleophilic addition, right? We've taken our nucleophile and we've added it to that carbonyl carbon. So this is along the same lines of all of our other nucleophilic addition reactions, with the exception of this weird intermediate here that has both positive and negative charges. And that's because we have those neutral conditions. But we said this carbonylamine isn't our product. It doesn't stop there, all right? So we got more steps that we can do here. All right, and I'm going to try to get you to fill in the missing gaps here. All right, there's one intermediate in between these two. But what happens is, in this molecule here, the oxygen and the nitrogen are kind of fighting each other over this carbon in the middle. The nitrogen wants to bring down its lone pair and kick off the oxygen. The oxygen wants to bring down its lone pair and kick off the nitrogen. They're kind of fighting over this carbon here, all right? And because we're going to see all these steps are reversible, but if we want to go in this direction, we have a ton of this amine around, so we kind of flip our free energy scale in favor of going in this direction. So the bottom line is the nitrogen's going to end up winning here, and we're going to get this nitrogen-carbon double bond. All right, give me 1 second. I'm just going to turn on the NMR. So try to get from A to B here. I will note that we said that this was neutral conditions. Those were our rules for our mechanism. But we said, truthfully, we're at pH like 5.5 or so. So there are some hydronium floating around, which is going to be important for this next step here. All right, so try to get me from this intermediate, our carbonylamine, to this weird carbon-nitrogen double bond thing we got going on here. All right, what bonds do we need to make? What bonds do we need to break? Right? Try to make it happen. All right, hint, hint, nudge, nudge that hydronium ion is going to be involved. Trying to get rid of that hydroxyl group, but it's a bad leaving group. How do we turn it into a better leaving group? By protonating it. All right, and so the last step here after we protonate it, how do we kick it off? Well, we're going to form that second carbon-nitrogen bond and kick off that leaving group all in one shot here, right? And that's how we get to that last intermediate. All right, our final product, we're just going to deprotonate this molecule. We need some base to do it. We're going to use our water molecule that we just created in the previous step. Oh, and now my nitrogen has a lone pair. And this product that we just created, we call an imine. I-M-I-N-E. So not amine with an A, but imine. And we're going to make note that we get this imine specifically when we react our aldehyde or ketone with a primary amine. So I'm going to title this section here, Primary Amines. All right, primary amines lead to this imine product. All right, everything starts off with, if we're talking about our reactions of aldehydes and ketones with nitrogen nucleophiles, everything starts off how we would expect. We have nucleophilic attack, and then we create our neutral nucleophilic addition. But then we have this weird continuation here where this nitrogen and this oxygen are fighting over this carbon, and the nitrogen will eventually kick that carbon off, replacing it with a carbon-nitrogen double bond. Right, so look at where we started with our ketone. We've taken this amine. Okay, let me actually just kind of sketch this out. All right, taking my ketone, my amine. If I'm going to do my product here, I'm replacing that oxygen with that nitrogen there, right? That's how I'm attaching these together. Replacing the oxygen with the nitrogen. Boom. That's how I get my imine product. Okay? So again, kind of visualizing it. Boom. All right? Now, we get a little bit of a different story if we use instead a secondary amine. All right, so I'm going to take my same ketone here. We'll stick with acetone. All right, but now I'm using a secondary amine. A secondary amine is when the nitrogen is bonded to two carbons. Different from how we kind of think about secondary alcohols when it's the oxygen that's bonded to a secondary carbon. A secondary amine means that you have two carbon-nitrogen bonds. That thing is huge. I don't know why I made it so big. All right, now I'm going to tell you the first few steps here are directly in analogy to what we did for our primary amines. So I want you to try to get me to that carbonyl amine intermediate. All right, and then after that, we again get that weird carbon-nitrogen double bond. Okay, so try to get me to this portion of our mechanism here. want you to try to do it on your own. I'm going to kind of quietly start filling this in so you can look up if you're stuck. All right, so I have my nucleophilic attack. I have this, weird intermediate that has a negatively charged oxygen and a positively charged nitrogen, and I make them both neutral by doing this proton transfer. All right, that gets me to my carbonyl amine. But again, now these two are fighting over one another, and eventually the nitrogen is going to kick off that oxygen. We're first going to take advantage of these slightly acidic conditions to make that hydroxyl group an even better leaving group by protonating it. And then we'll kick off that good leaving group by bringing down that pair of electrons from that nitrogen. All right, so same thing that we saw with our primary amines, but now we're using a secondary amine. But when we get to this point here, we're in a little bit of a different situation than where we were before. With our primary amine, we had this hydrogen that we could pluck off really easily in order to make our nitrogen neutral. That's not what I wanted to do. Here, we don't have that. So how are we going to get our nice, stable, neutral products? All right, what's going to happen is we have no hydrogen on our nitrogen to remove, so we're going to be removing a hydrogen from a neighboring carbon. All right, we're going to use our water proton acceptor here, weak base. That makes this pair of electrons come back down, allows that pair to jump up onto that nitrogen. So everybody take a second and draw me the product. What is the result of all these electron pushing arrows here? What did this arrow do? Cool, you're missing one more arrow that breaks that nitrogen. Yep. So what did this arrow do? And where did that pair of electrons go? No, so importantly, it just swings around. So electrons can't really like jump from one to another. This would be a bond breaking and formation arrow. So there's no lone pair that just sit there. It's a bond that forms between those two carbons. So carbon-carbon double bond. Awesome. Okay. So This arrow here broke that carbon-nitrogen double bond, so that pair of electrons is now a lone pair on that nitrogen. So I'm going to get rid of this. This is a lone pair. All right, my hydrogen got pulled off of this carbon here, but importantly, this arrow here is a bond-breaking slash formation arrow, creating a new carbon-carbon double bond here, creating what we call an ene-amine. Ene, why is it an ene-amine? Right, the ene because of the carbon-carbon double bond, the amine because of the amine group. All right, so our secondary amines, they don't form the imines, they form ene-amines. All right, we're actually going to see these enamines come up again later in the course. They're kind of special little nucleophiles. They react with specific electrophiles, and we'll talk about that. We'll cross that bridge when we come to it. But we will see these enamines again. They turn out to be quite useful. Cool. All right, so we're going to sort of summarize things here at the end. But we got a few more reactions of aldehydes and ketones to learn. And we're going to throw these into this bucket of what I'm just going to call other reactions. Okay. The first one is what's called a Wolff-Kishner reduction. All right, so we're talking about, this is our chapter on aldehydes and ketones, so I'm talking about starting with an aldehyde or ketone. And if I'm going to reduce this aldehyde or ketone, what am I going to do? What do we mean by reduction reactions? I'm going to make those carbon-oxygen bonds into carbon-hydrogen bonds, right? That would be reducing that carbon. And we talked about how we can use lithium aluminum hydride. We have these various things that we could use to reduce this to an alcohol. A Wolff-Kishner reaction is how you fully reduce an aldehyde or ketone, replacing both of those carbon-oxygen bonds with carbon-hydrogen bonds. Creating what? What's our functional group now? An alkane, all right? So it's a way to effectively chop off, that carbonyl oxygen. All right, so how do we do it? We use H2NNH2. All right, if we want to draw the Lewis structure of this molecule here, those two nitrogens are bonded to one another. All right, this is what's called hydrazine. Okay, so noting that hydrazine is just a primary amine, everybody's going to take a second and draw me the product of the first step in this reaction. We talked about how primary amines react with aldehydes and ketones. Considering hydrazine is just a primary amine, give me that product, that first step. right, primary amines, what do they do with aldehydes and ketones? They form what? What do we call them? The imines with an I. So now we have a carbon-nitrogen double bond. And this nitrogen just happens to be bonded to another nitrogen. All right, now in the second step, we're going to add in sodium hydroxide. All right, we're not really going to do our mechanism here, but suffice it to say that the sodium hydroxide pulls these hydrogens off of this nitrogen over here, allowing the nitrogen to react with itself and come off as N2 gas. So we have this really strong entropy push here because of this nitrogen gas that's formed in this reduction reaction. All right, but here's our Wolff-Kishner reduction. Treating an aldehyde or ketone with hydrazine followed up by sodium hydroxide. That will fully reduce that aldehyde or ketone to an alkane. The next one is what's called a Wittig reaction. All right, and whereas the Wolff-Kishner reaction converted our aldehyde or ketone into an alkane, our Wittig reaction will convert our aldehyde or ketone into an alkene. All right, so what we're going to do is we're going to take this carbon-oxygen double bond and we're going to replace it with a carbon-carbon double bond. Okay. Now, what do we use to do it? We got this fancy little reagent that we use. So triphenyl phosphorus. What do I mean by phenyl? Yeah, so phenol with the OL is that benzene ring with that hydroxyl group. But phenyl with a YL is just a benzene ring. All right, that's how you refer to benzene like as a substituent, is as a phenyl ring. All right, so you'll hear this term thrown around a bunch. So this is phosphorus. I'm just going to sketch it out real quick. This is phosphorus bonded to 3 big old benzene rings. All right, so that's this triphenyl phosphorus. It turns out that since phosphorus is one of those larger elements, it can have an expanded octet. It can fit 2 more pairs of electrons and get bonded to some alkyl group. All right, this thing here, this special little reagent is what's called an ylide. So a Wittig reaction is where you take an aldehyde or ketone, you react it with an ylide, and you get this alkene product where you've added whatever your R group is from your ylide in place of your oxygen in your aldehyde or ketone. All right, so if we just want to do an example here, let's take a specific aldehyde or ketone. Been using acetone a lot. Let's switch it up. All right, I got 6 carbons in my original ketone. How many carbons are going to be in my product?
6. All 7.
How many carbons are in this E-line?
1, 2, 3.
1, 2, 3. So 1, 2, 3 plus 6 would be 9. There we go. All right, so I'm going to add those 3 carbons at that double bond, right? Replacing my oxygen in my ketone for my R group in my E-line here. Cool. All right, and the last one is what's called a Baeyer-Villiger, although I always say Baeyer-Villiger. Reaction. All right, so first of all, let's remember that we've talked about these reagents before, these peroxy acids. And especially when we're talking about alkenes, we like to use a specific one, MCPBA. And what do these do for us? They're going to make epoxides. All right, so this peroxy acid what it did was it inserted an oxygen in between this existing carbon-carbon bond. All right? And that's what these peroxy acids do really well. And so what we're going to see with our aldehyde and ketone again, now we're going to use that same reagent, our peroxy acid. And it's going to do a very similar function. It's going to insert an oxygen between this existing carbon-carbon bond. All right, so I'm going to have as my product here, now there's going to be an oxygen between those 2 carbons. I've created what functional group here? Ester. Okay. Now in this case, for this particular ketone, acetone, it wouldn't have mattered which side I chose, right? I would have got the same product regardless of which side I chose. But what if we have some sort of a asymmetrical ketone or aldehyde? What's going to be my ester product? All right, so in order to figure it out, and I'm not going to make you memorize this, I'm going to give it to you on a constants page here. But for these Baeyer-Villiger reactions, we have what we call a migration potential. All right, and the highest migration potential would be if it was a hydrogen attached to that carbonyl carbon. So if you had an aldehyde, the oxygen would be inserted between the carbon and the hydrogen. All right, and from there it goes roughly in order of degree of substitution. We have our quaternary carbons, then tertiary carbons, as well as those phenyl groups are tied, followed by secondary carbons, and then finally, the least likely to migrate are primary carbons. Okay, so in order to figure out where my oxygen's going to go, I'm going to look at these 2 carbons that are bonded to that carbonyl carbon. I'm going to say, all right, this one's a primary carbon, and this one's a tertiary carbon. So which one has the greatest migration potential? The tertiary is higher on my list here. That means that the oxygen is going to insert itself between that tertiary carbon and the carbonyl carbon. Boom. All right, let's do 2 more practices using these peroxy acids. Where are you going to insert your oxygen? So between what? It's going to be between a carbonyl carbon and its neighboring carbons. So you're going to need to put an oxygen between these 2 carbons here.
Because this is an aldehyde.
Yeah.
And the H is high priority.
Yeah.
So,
Yeah.
wait, does it break the ring?
It doesn't. You still, yeah, something like this. You still have a ring. It's just now one bigger. So this is our highest migration potential is a hydrogen, and aldehydes, they have those hydrogens coming off. No, it's between the ring, right? So between those carbons.
I don't even know how to draw, bro.
Yes.
Okay, and then that highest migration potential hydrogen. Remember that aldehyde has that hydrogen. And it's, yeah, so keep going. It'll look pretty normal. And then what's going to be on the other side? Yep. So what do we make? Yeah. So where is it going to put the oxygen in between? So between the carbonyl carbon and that neighbor there. So the oxygen, you're just going to have now a bigger ring because there's going to be oxygen in that ring. Yeah. Although, you got to be careful. You lost a carbon going from here to here. Yeah, you lost a carbon too. Be careful. Oh, maybe not. Okay, I gotcha. It's very difficult to draw the 7-membered. Okay. So first of all, that very highest migration potential on our list was hydrogen. That's specifically referring to aldehydes that have that implied hydrogen bonded to their carbonyl carbon. So that means my oxygen is going to get inserted between this carbon-hydrogen bond here, creating what functional group? Carboxylic acids. All right, and I called this a Baeyer-Villiger reaction. Really, we could even be more specific. It is an oxidation reaction. It's another method of oxidizing our aldehydes and ketones. Okay, so then this one's super weird, all right? But following this same logic, we need to insert a oxygen between this carbon and this carbon, all right? So that means that we're going to, again, we keep our aldehyde or ketone, our carbonyl group. But now this is going to have this oxygen on this side, meaning we're going to grow our ring to be a 7-membered ring, which is always fun to draw. Boom. All right, this is now this cyclic ester structure here. These have a special name. They're called lactones. They turn out to be pretty important in biochemistry. You see them pretty often. All right. So that does it for all of our reactions from this chapter. So just to finish up, let's summarize by creating a giant reaction wheel here. All right, first of all, we learned how we could react our aldehyde or ketone with a nucleophile under basic conditions and acidic conditions. All right, we talked about how those nitrogen nucleophiles are special, so we could react with a primary amine, and we would get a little bit of a different product if instead we reacted with a secondary amine. And then we had those 3 more that we tacked on to the end, our Wolff-Kishner. Our one that I'm blanking on. What was the middle one? Oh, the Wittig. All right, and then lastly, that Baeyer-Villiger. All right, and then I'm going to put one more specific one on here. I'll tell you why in a second. All right, so this is just kind of a nice little convenient place to have all these reactions that we studied. Summarize, a good little cheat sheet. All right, making these are great little study tools. Complete our reaction wheel here. Yeah, that's okay. Doesn't have to be great. You can always point to a corner of the page or something. And in an ideal world, you really want to try to do as many of these as you can from memory, right? We always want to pull information from our short-term memory. That's how we signal to our brain that it's important to remember, that we need to hold on to it. They can even be good. We said that under acidic conditions we would be using those neutral nucleophiles. So let's say H and U instead. All right, so let's just kind of go in reverse order of what we had discussed. The last thing we discussed are these Baeyer-Villiger reactions. Baeyer-Villiger. All right, I'm going to need to go smaller. Where we're going to insert an oxygen in between those carbons, in between my carbonyl carbon and its neighbor. All right, our Wittig reactions are when we replace that carbon-oxygen double bond with a carbon-carbon double bond. Our Wolff-Kishner reactions, that's when we fully reduce that carbonyl carbon to an alkane. All right, the difference here, now our nitrogen nucleophiles, this is a secondary amine, whereas this one's a primary amine. Our secondary amine forms that enamine, where we have a carbon-carbon double bond, the ene, next to a carbon-nitrogen bond. Oops. My two R groups. Whereas primary amines will form that weird carbon-nitrogen double bond. Okay, So now we're going to get to these nucleophilic additions here. What was the difference between what happened under acidic and basic conditions? Let's rewind back to where we stacked these two next to each other. All right? Under acidic versus basic conditions, what's the difference? How many nucleophiles do I add under acidic conditions? 2. How many nucleophiles do I add under basic conditions? Just 1. All right, so that's why we wanted to put both conditions on our wheel here so we can kind of see side by side the difference. Basic nucleophiles will have that nucleophile added on, but we'll retain that OH from our carbonyl oxygen. Under acidic conditions, you end up getting 2 rounds of nucleophilic addition. So that's on there twice. All right, and then this is just a specific basic nucleophile here. That cyanide ion. And so I'm going to I'll draw out the full Lewis structure here. Basic nucleophile, so that gets attached. And I still retain that oxygen. All right, and what I'm going to tell you is I added this one specifically because next week we're going to cover 2 reactions of these nitrile groups here, but I'm going to punt on that until next week. Okay, so there's going to be 2 more that we're going to add to this wheel here. Okay, so I want to instead switch gears and start talking about exam material, so your chapter 17 and 18 material. Hopefully everybody saw my announcement about this next exam featuring chapter 17 and 18, so featuring alcohols, ethers, epoxides, thiols, and sulfides, but not aldehydes and ketones. All right, we haven't finished our discussion of aldehydes and ketones, and so I'm going to lump all that material together. Okay, so what I want to do is start reviewing, and we're going to rewind back to what was the furthest away, our chapter 17. So we're going to create an alcohol study guide. All right, or rather, I'm going to walk you through the process of how I would create a study guide for this chapter. Okay, because last unit we learned reactions, don't get me wrong, but we kind of learned only a few reactions, and we did them like really in depth, right? So that electrophilic aromatic substitution, it was just a lot of talk of the same reactions. Here it's kind of the opposite, where we have a bunch of different reactions, like a bunch of little reactions instead of one big one, all right? And I remember when I was studying for this course, when I was in your shoes, I get like really overwhelmed before exam time, just being like, I'm supposed to know everything about everything. What the hell? Like, what's going on here, right? And it's like, no, that's not how the course works. And the more that you can see the structure of the course, the better. So the first thing I want you to do is we're going to make a list of our alcohol reactions. All right, because I'm not asking you to know everything about everything. We can break it down into a few categories here, what it is that we're supposed to be able to do. And the more that you can like see that organization, and that's how you organize things in your brain, the better and less overwhelmed you'll be when it comes to studying. All right, so everybody's going to take a second, flip back through your notes, do as many as you can from memory. That would be awesome. All right, but let's make a list of all the reactions that we covered in that alcohols chapter. right, for right now, just make a list of those reactions. We'll do examples in our next step here. We'll kind of summarize with some examples. But right now, just break it down into those categories that we have.
Did you want the reagents or the actual?
No, we'll summarize that information in a second. Right now, I just want the categories. Pretty good.
Substitution.
Let me help you, Dr.
I don't know. Now that I'm looking closely at it, it seems a little haphazard.
Hold on. Yeah, that's why I was like trying my best.
Uh-oh.
I'll tell you why I should take the exam.
Yeah, there's
I'll tell you why,
catalyzed
I deserve it.
oxidation, hydrogenation.
Cool. All right. So throw me a category. What do we got? So acid catalyzed, oxymercuration, hydroboronation, those would all fall under the umbrella of our hydration of alkenes. So that was our first category. What's another one? Oxidation reduction. All right, what else? We got substitution of our alcohols. Okay, we had one more way to create alcohols as well. Grignard would be preparing our alcohols. And then we had our dehydration reactions as well. Okay, so it all seems very big and scary, but when we're going to break it down, think about these topics covered. These are our topics that we've covered here, right? So that's what we need to know. We don't need to know everything. We need to know these 5 things. Okay, so let's give ourselves a little bit more information here. So for example, when I'm talking about the hydration of alkenes, that means converting an alkene into an alcohol. All right, when I'm talking about oxidation or reduction, that's when we take our alcohol and we can oxidize it to an aldehyde or ketone, or we can go the other direction. All right, substitution is our way of taking that alcohol, turning that hydroxyl group into a better leaving group, and then substituting it for some nucleophile. So we can make a bunch of different stuff with that particular reaction, just depending on what nucleophile we use. All right, Grignard was when we take our aldehyde or ketone and make it into a bigger alcohol. All right, and then dehydration, we're actually going to be careful because we learned 2 different dehydration reactions depending on the chapter. In chapter 17, we learned about dehydration reactions under high heat that produce alkenes. But then under chapter 18, we learned that if you take those same conditions but use moderate heat, you instead get an ether. All right, both of those would fall under that umbrella of a dehydration reaction. All right, both use that same concentrated sulfuric acid, so we're going to be good and distinguish between our two levels of heat in terms of our product. All right. And so now what we're going to do is we're going to take a random alcohol and we're going to give ourselves an example from each of those categories. Some of these are ways to make alcohols. All right. Others are things we can do with alcohols. But you're going to grab an example from each one of those reactions and put down your specific reagents, right? Create this little summary reaction wheel here. Now you grab specific reagents. Did it pop or something?
I don't know.
I mean, did you bang it or did it?
No,
It was just
I was
in
doing
motion.
this, and I was like, oh, I can't go anymore.
Oh, that's nice.
¿Tienes algo?
Huh?
¿Tienes algo?
Tennis elbow?
Para tus conocidos, movidos por el mundo.
For real?
Yeah, but that's like a tendinitis thing. And then it just hurts in your elbow. Fortunately, it sounds like you pulled something.
I'm a doctor. You should take my advice.
I should. I should.
You start coming to
Whoa, you had to dinner first.
Alright, what are we doing?
I don't know. I haven't done the whole
So,
different conversation.
You can do whatever you want in your study guide. So yeah, you could do one example, or you could give me all of them that you could do that could make that alcohol. In this case, there's not a difference between them, right? Now they would work the same.
oh yeah,
How many carbons you got in that alcohol?
hold up.
It's cooking.
We're diluting this. 1, 2. There's only 2.
So then how many should be in your alkene?
2.
How many are in your alkene?
2. Oh, you talking about this guy?
Yeah.
I was looking at the other guy. I was
It was also
Look at the
a
light
lot
of
of
it.
it. I forgot how to do it.
No, it's like an equal sign.
I feel like I don't know how to use my body.
Let me help you. I'm a doctor.
You know when we were kids and they started getting
Uh-huh.
the freaking
Yeah, you like that?
the projectors and you had to calibrate it by touching the four corners?
Yeah,
I need a
that's like a
calibration
lot.
for it.
Oh,
I need to be
like on your-
calibrated.
on your controller.
No, in the classroom. In the classroom.
calibrate the touch.
Yeah,
Oh.
yeah.
You need to calibrate them on your whole
Yeah.
body.
Yeah, bro, I need to be calibrated, man. Good. I was literally doing this earlier and I forgot how.
Wait.
Now my fingers are annoying.
Well, I was just gonna do that. Should I make it right now?
Yeah.
Oh.
Yeah, make an ether. You can do a nucleophilic attack on this thing. You can make this thing with a Grignard.
I guess you're right. I'm not thinking. My third eye isn't open.
I'm gonna have to do a lot of stuff. Good. Salami cake.
This is a good time to start.
I'm gonna close your salami.
No.
Close.
I bet that's 25%. Chrysippus, why'd you start incorporating a new color? Last lecture you started using that bright green. I don't got that in my template.
I was trying to distinguish between the two greens.
You what?
I was just trying to distinguish between the two greens.
I don't have that in my template. It's been like 2 years.
You
Probably do.
Custom colors
Yeah,
on
add
footnotes,
colors.
right?
No, yeah, but I add them in based on what he's been using. So you always use
Yeah,
these
click on it.
for the last 2 years.
That's the overcharge.
And use this like one time.
Yeah, I mean,
Yeah,
okay,
definitely
don't
don't
get too
use
much
that.
shit.
And
It's
then-
like so
I could-
destroyed.
I could-
It's
Oh,
just
yours is
my
a
like.
I'm
Yeah,
having
but
that
I
destroyed in
I know. I keep my good
I can
charger
find it,
at
it's fine,
home.
but I was
This is
just
just
like,
my
I'm
like
not
really shitty charger
taking
that
all
everyone
of
just
You
it.
can
told me
take
'cause
your
I
own
needed it
creative
now.
liberties on your color usages.
I just use yours.
It works.
Well, I'm stumped now. I ran out.
It's just.
Oh, yeah, yours
This
is
is
better.
why I don't.
And then you can do
All
whatever
right.
you do. You get the custom ones.
Probably.
And we got our 2 dehydrations.
Color coordination actually helps a lot.
I'm just saying, just like
Huh?
Not these ones.
Do you color coordinate?
All right, so if I was going to do a reduction reaction, that means I'm starting with an aldehyde to reduce that to ethanol. And we got a few reduction reagents we can use. In this case, we could use either our strong or our weak. So I'm just going to pick one. All right, hydration reaction would be starting with a 2-carbon alkene. I could pick any one of my hydration reagents. I could even list all 3 here if I wanted to for study purposes. Just for the sake of time here, we're going to say our concentrated H2SO4. All right, a Grignard. How would we make this particular molecule with a Grignard?
double bonded out.
So we would have what's called formaldehyde. Your smallest possible aldehyde. And we would react that with a methyl Grignard. To create this ethanol. All right, oxidation. We'd have 2 oxidation agents, or yeah, we could do 2 of them here. One using our weak oxidizer like PCC, or our strong oxidizer like sodium dichromate. Our weak oxidizer would give us what functional group? An aldehyde. Whereas our strong oxidizer would give us what functional group? Carboxylic acid. All right, substitution. We can even break this up into the 2 steps we learned. One being turning it into a better leaving group. In this case, I would be turning it into an alkyl chloride. All right, and then from there, we're going to treat it with some nucleophile and get a substitution reaction. All right, and we had our 2 dehydration reactions, both of which use that concentrated H2SO4, but one uses high heat, and the other one uses moderate heat. Under high heat, we get that alkene product, whereas moderate heat, would produce that ether product. All right, so boom, I made a list of the reactions that we covered, and then I gave myself a little reaction wheel with a few examples on there. And again, just a great way to study for this exam. You know, we could swap out. There are other reduction agents, so maybe we want to make a new wheel where we try to use different reagents. All right, we'll use our other reducing agent. We could use this other one. This was a particularly small alcohol. We could replace the alcohol in the middle here and then fill out the wheel again. That'd be another good way to practice, right? So just kind of summarizing things, the last thing that we want to make sure to note is that a few of these I would want to go through and put a big star next to because I should know my mechanisms for. And so I'd want to practice my mechanisms here for these reactions. Okay, not all of them we do. Yeah, these ones, yeah. Our dehydration. Remember, Grignard and the hydrides were very, very similar. This reaction is just the reverse of this reaction. All right, so those mechanisms are very closely related as well. And this one is pretty similar to this, except for you have nucleophilic attack instead of elimination. But yes, all these here we would want to practice our mechanisms for. Cool. So on Tuesday of next week, we'll have a review session. We're just going to do as many practice problems as we can in that time period. On Thursday of next week is when you'll be having your exam. Again, the exam will be on alcohols, ethers, epoxides, thiols, and sulfides. Cool.